If rendering is all about flattening a 3D world into a two-dimensional image, how do we actually achieve that? Perhaps if I take this lovely egg here, I can use a clear sheet of plexiglass to just crush it flat. Voila! Look! A beautifully rendered scene. It really captures what the original looked like, doesn't it? Now let's try the same thing with this teapot.
AJ, no! There's a better way.
Flattening the 3D world into 2D is something people tend to be familiar with because they've used cameras before. So how does my phone camera capture the world in front of me and collapse it onto the flat phone screen? Well, first, particles of light called photons leave the sun. Or maybe a light bulb if I was indoors. Those photons stream into the world in front of me, bouncing off of objects in all different directions. Some photons bounce among multiple objects, altering their color as they encounter different materials. And from all the photons bouncing all over the world, eventually some of them collide with my camera lens, bringing with them a record of everything they touched. Inside the lens of the camera is a tiny rectangular sensor which receives an electric signal when a photon collides with it. The sensor accumulates billions of photon collisions in an instant and saves them as an image. This is by and large the way that the human eye works as well. Instead of using an electronic sensor, our eyes use light-sensitive cells and optical neurons to translate photon collisions into an image. So when researchers first started considering how to create an image of a 3D environment in computer graphics software, it made sense for them to start from a similar place. With one important difference. In the real world, so many photons are whipping around us all the time. The number of photons around us is just uncountably large. It's estimated that on a bright day, our eyes encounter more than 1 trillion photons per second. In a computer, it might take decades to calculate the paths of 1 trillion photons, and that's just for 1 second of video. That's why the algorithms that create images on a computer need to be much more prudent about the light rays they calculate. Ray tracing is the process researchers invented to follow virtual light rays emitted by a virtual light source that eventually arrive in the virtual image sensor of a virtual camera. But the true genius of ray tracing is that it discards all the lighting information in a scene that is not useful to the final image. How does it do this? Well, imagine if we started our calculation at the light source, the virtual sun. One light ray at a time would leave the sun and bounce off the ground and off objects in the scene, and we would keep following the ray's path until it disappeared into the infinite distance or it hit the camera lens. But how many of these light rays are going to hit the lens? Almost none of them. This scheme is hugely wasteful of our precious computer time. Instead, ray tracing works backwards. It assumes that a light ray must have collided with every pixel in the final image in order for the pixels to have any color at all. And therefore, it follows each of those light rays from the camera lens through the pixel position on the image plane back into the scene. These backward light rays bounce off objects in reverse, acquiring the material colors of the objects, and eventually they arrive back at the light source from whence they came. The nice thing about calculating light rays that are connected to pixels is that it is a huge reduction in the number of light rays hitting the image. Most modern images have millions of pixels, so we are calculating millions of light rays instead of trillions. There are many variations on ray tracing algorithms. Some versions do a better job replicating soft lighting, and others better mimic real-world camera lenses. These algorithms get more complex as more real-world effects are incorporated, but the basic concept of following light backward from the camera remains the same. But wait, let's go back a bit. What if those backward rays bounce around and shoot off to infinity and never arrive at a light source ever? That's easy. The pixel you started from never received any light in the first place, so you color the pixel black. The absence of light is black, but all other colors come from some kind of light source. The light source may have had its own initial color and brightness, but each light ray gets modified by the materials of the objects it interacts with. This begs yet another question. How do different types of materials affect how rays travel through the scene? Plastic is shiny, so a light ray that bounces off of it will stay bright, but will also inherit the plastic's color. Velvet will absorb most of the light and reflect very little brightness or color. Glass is translucent, so light rays might travel straight through it. And aluminum is reflective, so light rays may not change color very much and instead keep the color of whatever they last bounced off of. In computer graphics, we describe objects' materials with shaders. Shaders tell ray tracing software what an object should look like, including its color, how shiny it is, how opaque it is, and more. Shaders can be used to do a variety of tasks, but most of the time they are used just to establish some basic material parameters like color, texture, reflection, and refraction. It's also good to know that most shaders are super efficient approximations of the physical world. In the physical world, these material parameters might be the result of super thin layers of paint, or tiny hairs, or molecular irregularities. Calculating light rays interacting with individual hairs or atoms on an object would be extremely costly though, and that level of detail is usually not necessary to make the material appear realistic. You would be hard-pressed to find a material for which there is not an approximate but totally satisfactory industry standard shader. While the nuances of ray tracers and shaders can consume an entire career, it's important to understand these core components of any computer graphics framework. That understanding will help you optimize your use of time and computer resources, it will help you decipher visual errors in your imagery, and it will allow you to invent solutions to problems that may have never been solved before. Fun fact: there's an annual competition called Shader Toy for expert shader authors to flex their muscle. The competition is judged by who can make the coolest looking shader with the smallest file size. In the past, these competitors have created whole oceans, translucent snails, and whole video games in files so small they can fit into 240 alphanumeric characters.